Hey everybody, happy Monday. Jonah here, back with another video as we move into day number 4 of Severe Weather Awareness Week. Today's big focus is going to be on tornadoes. So I'm briefly going to discuss the tornado drill that's going to occur later today. We'll talk about what tornadoes are and what tornadoes look like, especially what tornadoes might look like in the state of Michigan, and how we detect tornadoes. So very quickly, the statewide tornado drill is this afternoon at 1 p.m. You're definitely encouraged to participate in this tornado drill. Go ahead and use it as an opportunity to exercise your tornado safety plan. Get into a safe place, an interior room on the lowest floor of a building, away from doors and windows. So that's a basement or an interior hall closet, an interior bathroom, a storm shelter, a storm cellar. We definitely don't want to be on the upper levels of a home or a building. We don't want to be outside, and we don't want to be in a car or a mobile home. So definitely you'll want to be in a safe place. Take this opportunity to practice that tornado procedure, and just act as if you're under a tornado warning at 1 p.m. this afternoon. We won't really dive into more about sheltering from tornadoes today, but we will talk more about that on Saturday. But this should give you a basic opportunity to at least practice going to the location where you need to be. And we'll talk more about what needs to be at your location on Saturday. So what are tornadoes? Tornadoes are rapidly rotating, violent columns of air, and there's two criteria that must be met for a funnel cloud or a gustnado or anything like that to be defined as a tornado. Number one, it must be in contact with a thunderstorm base. So a funnel cloud would be attached to a thunderstorm base, but it would not necessarily be a tornado until that second criteria is met and it is in contact with the ground. Whereas a gustnado is in contact with the ground, sort of like a leaf tornado is, but it is not in contact with a thunderstorm base. So both of those things must apply. It must be in contact with a thunderstorm base, and it must be in contact with the ground for it to be a tornado. And tornadoes can bring destructive winds from as low as 80 miles per hour to over 300 miles per hour. And for those of you that watched our video yesterday, you'll know that the severe thunderstorm warnings we were talking about, there's 3 tags, and that highest tag can bring winds at or above 80 miles an hour. So at the lowest end of this scale, we're talking about destructive winds that can blow debris through the air, can significantly impact trees, vehicles, high profile vehicles especially, mobile homes. All of those things can be impacted by winds of this speed, and of course it only goes up from there. And unfortunately, we can start to see some pretty significant tree damage, significant damage to homes. And then at the higher end of the scale here, of course, we have all seen examples in Joplin, Missouri, Mayfield, Kentucky, Moore, Oklahoma in 1999 and again in 2013 of what these tornadoes with these types of wind speeds can do to a community. And Michigan is no stranger to that. We talked about the 1965 Hudsonville tornado on Sunday when we first started Severe Weather Awareness Week, and thankfully we haven't had anything of that significance in Michigan since then, but it is certainly possible. And again, it's not a question of if that will happen again, it's a question of when something like that will happen again. And that's why we really stress being weather aware, and knowing that there's severe weather risks ahead of a severe weather event. And the biggest reason we're doing this tornado drill today is to give folks an opportunity to practice those plans. So go ahead and participate. If you are not ready to go, that's okay. Definitely use this week to get ready. And we'll talk more about how to get ready on Friday and Saturday. An average of 16 tornadoes occur in Michigan each year, and an average of 71 fatalities occur in the United States every year. This number, the 71 fatalities here, is a great improvement when we compare to years as recent as 2000 and then all the way dating back 1990, 80s, 70s, all the way back into the 50s and 60s prior to when tornado warnings were a thing. And we finally got the first official tornado warning from Tinker Air Force Base back in the 1940s or 50s. And unfortunately, tornadoes killed hundreds of people every single year on average. And this is a great improvement. The National Weather Service has done an amazing job of warning people, reducing the number of false warnings, false alarms, and improving their reach. Social media has been a big thing, and we want to be part of that catalyst that continues to bring this number down. And you can help with that as well by making sure that other people are aware of a severe weather risk. Share your local National Weather Service posts with those around you. Share our posts with those around you. Make sure everyone you know and you care about has some way to get weather alerts, be it a phone, a weather radio. A weather radio is a great thing to have. Don't be one of these statistics here. Make sure that you're weather aware and that you have a way to protect yourself from tornadoes and other severe weather hazards. And then this year features a global weather pattern that may lead to a more favorable and a more above average severe weather season for the state of Michigan and the Great Lakes at large. We're going to be moving from a strong El Nino pattern to a La Nina pattern by mid to late summer. And I won't dive into exactly what all that means, but we typically see an increase in severe weather potential during this type of a transition period. And so it's definitely something this year to pay close attention to. I'm not saying there's going to be more tornadoes. We're not forecasting specific areas that are going to be at a higher risk of tornadoes. We're not doing any of those things. We're just saying that the global weather pattern may lead to a more active severe weather season here in the Great Lakes and in Michigan. So it's a good year to be weather aware. So what do tornadoes look like? And we're going to go through a couple of slides here and we're going to play a little game. So I want you to take a look at the first image in every sequence and see if you can guess where the tornado is. And this one is pretty easy, so let's see if we can guess where the tornado is. And for those of you who said right in the middle of the picture, yeah, you're right. The tornado is located right here, center frame. We've got beautiful high contrast lighting, presumably based off this refraction in the clouds here. I'm going to say the sun is off over here. And it's really providing some nice high contrast lighting. We've got a nice rain-free base, precipitation-free base here, with the tornado is not becoming obscured by rain or anything. It's late afternoon, early evening as the sun sets, so plenty of lighting to see this tornado. And we see it's in contact with the thunderstorm base, and it's in contact with the ground, and it's even spraying debris and dirt up into the air, and it's even taken on a little bit of a red hue, and that's mainly from the sun, but I'm also going to assume that this tornado is in the southern plains of the United States, and red clay is also very popular, or very common rather, down in that area. So let's take a look at this photo, and let's see where the tornado is in this one. So for those of you who sat on the left to left center of the screen there, you're absolutely right. The tornado is located right in here. We see an area of darker material as compared to this area and this area over here. And this is what would be known as our condensation funnel. So this is your typical funnel of a tornado, known as the condensation funnel, and it's in contact with the ground and it's in contact with the thunderstorm base. The thunderstorm base is actually probably off frame here, but this image is taken in such close proximity that it cuts that off. And then we see the tornado wind field, or what is ground debris, being sprayed up here. This is likely still the tornado wind field. In fact, the person who took this picture is so close to this tornado that he or she is probably within the tornado wind field as well. So they're within the circulation of the tornado. They're just not in the condensation funnel. And thankfully, as far as we know, this person was not hurt or injured or killed by this tornado. But this image does a great job of highlighting how close this person is to this tornado and how difficult it is to see, even at this close range. Yeah, sure, if you look at it long enough, you can see this wedge or stovepipe tornado in the picture here. But at first glance, when you're doing other things, when you're driving down the road, when you're coming home from work or that party, and you're just driving down the road, you may not be thinking that this is a tornado. It kind of just looks like a black mass of storm that's in front of you. And it doesn't necessarily look like a tornado at first glance, and obviously this image has been brightened and it's been enhanced to some degree, but certainly a tornado is right there in the frame and is pretty difficult to spot at first glance. Let's take a look at this one, see if you can find the tornado in this image. And again, this one happens to be in the center bottom of the picture here. And it's a little bit hazy, but we can see right through here we have this area of darkness back in the rain. That is indeed our tornado. And it looks like we may even have another funnel or another sort of circulation right here as well. But the tornado is definitely ongoing. We can see that it's all the way down to the ground, and it's obviously in contact with this thunderstorm base up above. And we don't see any damage, but it's obviously definitely on the ground and is becoming or is already obscured to some degree, at least by rain. And we'll show an example of what that looks like on radar. But what's happening is the tornado is spinning around and it's pulling the rain from the storm, the rain and hail from the core of the storm back around, and it's looping in on itself. And it's just creating this curtain of rain around the tornado, obscuring the tornado from view. And if you're driving towards this or you're looking out your window at this, you're going to have a very hard time seeing the tornado. The tornado can become invisible to the naked eye when it's obscured by rain like this. So let's take a look at this image. This is definitely the hardest image, but see if you can find the tornado in this image. So the tornado in this image is actually way back in here, and it's entirely visible to the naked eye. We have radar scans from this time of when this photo was took of a debris ball, and we'll show what that looks like on radar, but the debris ball was about a half a mile back in the rain here in this direction. And that was the tornado ongoing and throwing debris up in the air, and the radar was picking that up. totally invisible to the naked eye. You can't see this tornado at all. It's entirely rain wrapped. Presumably, this is late evening. The sun is probably going down. There's not a great deal of daylight left. And this tornado is totally invisible to the naked eye. And you'd never know that there was a tornado back in this mass of clouds and rain. And so that is what tornadoes look like. And unfortunately, those last 2 or 3 images that we looked at are what tornadoes are really going to look like, or rather what they're not going to look like, if you will, in Michigan. The simple fact is that in Michigan, one of 4 things happens. Number one, tornadoes in Michigan are typically very brief. Our radars, the National Weather Service WSR 88D model radars, take a scan of the storm every 3 to 4 to maybe 5 minutes. And some rotation signatures that are there on one scan are not there on the next scan, and oftentimes we find that tornadoes are so brief in Michigan that they only last for a few minutes, and that radar scan will miss it by the next time it comes around and scans that storm. So we'll talk about that in a minute, but that's one of the first things, is that tornadoes in Michigan are typically brief. Obviously they can be longer, but typically they're pretty brief tornadoes. And so that does a couple of things. One, it makes them hard for radar to pick up. And number 2, it makes them hard to warn and hard to take shelter from, because they only last for a few minutes most of the time. The second thing about tornadoes in Michigan is they are often rain wrapped. We often have storm modes that are messy. We get a lot of tornadoes that are embedded with lines of storms. We don't have those typical discrete supercell storms that are producing tornadoes. And if we do, they're often accompanied by heavy precipitation. And so a tornado can often be obscured by rain and hail and be almost invisible to the naked eye, as we saw in those last 2 images that we looked at. The next way that tornadoes are very hard to detect in Michigan is because a lot of our storms, a lot of our severe weather occurs in the late evening to overnight hours. And that can further hinder our ability to see tornadoes. Tornadoes at night are very difficult to spot, especially if they're also rain wrapped. And so that's why we encourage folks, when we're under tornado warnings, do not wait to see a tornado, do not wait to hear a tornado. Just go to your safe place, get there as soon as you possibly can. And just wait for the all clear. Do not wait to try to see that tornado out of your window before you go and take cover. It may be impossible to see. And then that first image we looked at was a big, beautiful tornado with high contrast lighting in the sunset in the Great Plains of the U.S., away from rain, away from traffic and trees and urban infrastructure. That is not always the case in Michigan. In fact, most of the time that is not the case in Michigan. We have a lot of urbanization going on within Michigan and a lot of changes in elevation. We have rivers and lakes and the Great Lakes and all of those subsidiary waterways that feed those, and our terrain changes quite a bit to accommodate the Grand River, the Kalamazoo River, all of those rivers that flow down towards Lake Michigan. We get very low in terms of our elevation as compared to the Great Plains. And so we need to be aware that hills are going to block our view of tornadoes and storms in general. Trees are going to block our view of storms and tornadoes. and make them very difficult to see. That's one thing that Owen and I have. It's our biggest struggle when we're storm chasing in Michigan is finding an area that's clear to view tornadoes and storms and storm structure. And we even use drones, and even those sometimes have a hard time of getting up above the trees and getting us views of storms and potential tornadoes. So it's definitely a struggle, and please don't try to do that. Please just go and take cover, and don't wait to see or hear that tornado before you take cover. So we talked about how radar, and this is that WSR 88D model radar that the National Weather Service uses that I mentioned earlier to detect storms. And what this does essentially is it shoots a beam out of the radar dish, and it shoots it out and it picks up precipitation, raindrops, snowflakes if it's winter, hail and a thunderstorm, etc. And it sends that energy back to the radar, and then that energy is read by a computer, and it spits out our classic green, yellow, and red and pink colors on radar. And that is based on the volume and the shape of the particles that is reflected back to the radar. And then again, it notes that this is a rotating radar antenna. So this is spinning in a circle very slowly. It only sees each area every 3 to 4 to maybe 5 minutes, as I said. And so sometimes we miss those tornado signatures on radar, or if they are there, they're often only there for one scan or something like that. So it's very hard to detect tornadoes in Michigan when we have all of these quick hitting, brief tornadoes. And this is an example of the Birmingham, Alabama radar site and its reflectivity picture of a storm. And the radar site is back over here near Birmingham, Alabama. And we're looking at this ongoing supercell. And this is your classic, tornado producing supercell. Very clear radar presentation here. We have our storm that's very much spread out. We call this a flying eagle. It's very spread out. And then we have our intense hail core, rain core back in this area here. And then this would be our tornado. Our tornado is right in this area here. And this is this sort of hook shape is what's known as a hook echo on radar. And this is caused because the tornado that's ongoing in this area here is pulling precipitation out of this core. So it's pulling rain and hail out of this core, and it's pulling it back on itself and then feeding it back into the storm. So we get this hook shape here of precipitation being pulled out of the storm and being fed back into it as it loops around the rear flank downdraft and the tornado circulation. So that's what is going on here. And then this reflectivity signature is even giving us what's known as a debris ball. So this is where our tornado would be. And what's happening is the tornado is lofting debris from the ground, and it's throwing it up into the air. And the radar that's back over here is sending out its beam, and it's picking up this precipitation. And then it gets to this area, and it's picking up debris. And the computer at the radar site doesn't know that this is debris. It just thinks that, wow, this is a lot of hail. And so it's showing that as pink and a little speck of white there on the radar. And so that's what's known as a debris ball or a tornado debris signature. This next picture is from the National Weather Service in Norman, Oklahoma, and their radar site just to the east of Moore, Oklahoma. Here's the radar, and this is looking at a storm, and these are the winds of the storm. This is a product known as velocity, and this is looking at what the winds in the storm are doing. So it's taking that precipitation, and it's measuring how fast that precipitation is moving, and those precipitation movements are driven by the winds of the storm. And so it's displaying values of wind speed here. The light red colors are lower wind speeds, the lighter green colors are lower wind speeds, and then the brighter the color, the brighter, or the faster the winds, excuse me. So red are winds moving away from the radar, and green are winds moving towards the radar site. And so we have an area here of very bright greens and even into blues. And then we have an area of very bright reds into pinks and even whites. And they are very close to each other. And so what this is showing us is that there's winds in very close proximity moving very fast in opposite directions. And this is what's known as a tornado vortex signature, where we have winds very close to each other, very strong winds, very close to each other, moving in opposite direction from the radar. And what's actually happening here is this is where our tornado is. So there is a tornado ongoing here in this radar frame. And it's producing damage, but the radar is picking up these winds, and this is where our tornado is, right in here, where those velocities come together, and we have what's known as a velocity couplet. The final big radar product that's used to detect tornadoes, there are others, but the final one that's used to detect tornadoes is what's known as correlation coefficient. And in basic terms, the radar beam is going out, it's detecting the precipitation or debris, and it's coming back to the radar, and the computer says, okay, how similar are the different particles that I just analyzed? How similar are they to the particles that are around them? And when they're similar, so if you have a bunch of raindrops, they're going to be very similar, and that value will be very close to 1 or 100% relation. And once you start to throw different particles in there, such as hail, hail is very rarely the same size as all the other hail around it, and so you start to have little drops in that correlation to other particles around it, and so you will start to see what's known as a correlation coefficient drop, or a CC drop. And that's shown by these yellows and greens and into these light blue colors. And then once you start to throw debris up into the air, once we start to see 2x4s, parts of people's homes, businesses, cars being thrown up into the air, and the radar is picking those things up, obviously those things are very different in sizes, and we see a big drop in the correlation to other particles that the radar may be picking up. So we get what's known again as a CC drop, and in this case where we have a big ball, we would need to correlate this to velocity and reflectivity. But in this case right here, we have a tornado ongoing, and it's lofting mostly trees up into the air in this frame, and we're seeing that CC drop, or that tornado debris signature, right in that area there. So those are the main ways that we detect tornadoes using radar. The next way is a little bit more human involved, and you can help with this. So storm observers, or storm spotters, and storm chasers as well, are big key parts in severe weather warning, and especially in the tornado warning process. And you can be a part of this. So you can sign up to be trained to report severe weather in a safe manner. And the best way you can do this is by attending a training from your local National Weather Service office. This is the Weather Service in Grand Rapids, and the training schedule that they're offering this year. A couple of these have already passed, but I will have this up here for all of you to take a quick screenshot of if you're interested in signing up. There's more information at this link here. And this is for the National Weather Service in northern Indiana for our southern counties in Michigan that we cover. The link to sign up and get more information is right here at the bottom of that orange box there. So I definitely encourage you all to sign up. It does not involve any money. It does not involve any unnecessary risks. You just have to, from the safety of your home, report any weather that occurs at your home. So hail, wind, tornadoes. You don't even have to do it when the storm is ongoing. You can do it after the storm. They just need to get those reports, and you can help be part of that warning process and help your community stay safe. So that's going to do it for our Severe Weather Awareness Week video for today on tornadoes. Just a quick reminder, we do have the statewide tornado drill today at 1 p.m. So you may hear tornado sirens in your area. Your phone may go off with an emergency alert. Your weather apps on your phone may alert you that there's a drill. If you have a NOAA weather radio, that's more than likely going to go off this afternoon as well. So please make an effort to participate in this tornado. If you're at work or at school and you're not participating in the drill and in your workplace or at your school, at least take a minute and think about, hey, this is where I'm going to go if there was actually a tornado at this point. So use this opportunity again. This year could be a little bit more of an above average severe weather year for Michigan. So definitely a year to be weather aware and prepared for severe weather. We'll have more information about tornado sheltering and how to prepare for severe weather and tornadoes on Friday and Saturday. And make sure you guys continue to check in at www.westmichiganweather.net/information and safety. Thank you all.